In the Pelkey and Miller handouts for E1 elimination, there are a bit of possibly incongruent messages, and one is that Professor Pelkey states that Zaitsevs are favored. The Zaitsev products are the major products because the more stable double bond is going to be the favored product. And then Miller is at some points to stress that this is going to be an unselected process. And though those two sound like they're in some tension, they're actually not. Basically, the message is that yes, you're going to make more of the Zaitsev than anything else, but you should anticipate that these products simply make everything, and that's because you're going to go through a high energy intermediate that is simply not going to be that discriminating when it reacts further. Now, if you have a mechanism problem like, say, this one, or even a predictive products problem, this would be a case where I would draw out the mechanism. But you really ought to start by taking whatever reagents are around the arrow and drawing them out in line angle or Lewis structure form. So the first thing I do to start the problem is to begin by drawing out the sulfuric acid in its Lewis structure form and also the water, and hopefully that will spark ideas about what might happen next. If I'm looking at the original starting material, I don't see a leaving group at the moment, but I do see an alcohol, and I know that in the presence of an acid, I can convert that alcohol into a better leaving group than it is right now. Right now, it can't leave. It won't leave as O- because it's a terrible leaving group. That's a pKa of 16. It's not good enough to leave on its own. Plus, in the presence of acid, I'm not going to form an O-. But in any event, I could convert this first into a better leaving group. Not a good one, but a better one, and then maybe other chemistry can happen. But if I'm looking at the reaction conditions and sizing up what's likely to happen first, what I'll note here is the presence of heat biasing me toward elimination, the presence of acid making my nucleophiles weaker, again biasing me toward elimination. I suspect I'm going to see some elimination products. If I would like to turn this alcohol into a better leaving group, it needs to pick up a proton first, and so what I'm going to do is abstract a proton from a nearby strong acid. Or alternatively, I could have the water and the strong acid react first, and then transfer the proton that way. The original pKa of the system was 16 up here. The pKa has now been converted into a -2 for this oxygen. More importantly, this originally was going to leave as an O-, and now would leave as a neutral O. So this is now plausible. It's in the right range. So now let's just simply have the water leave. And at this stage, what I have is a carbocation intermediate, and of course the water could come in at this point and re-attack, which both heads back the way it came and also generates the racemic product at this point. So one thing that I'm definitely forming in the final analysis is going to be both enantiomers of the original starting material. I had a single enantiomer originally. At this point, if water were to attack, it could attack from the wrong side. So I'm going to be making the 50-50 mix here. And again, this is not necessarily a new product, but what I've done is destroy the starting material stereochemistry. So what else could happen at this stage? Well, I have a carbocation at the alpha position, and I have hydrogens at this beta position, and I have no hydrogens at all at this beta position. So if the water was headed toward the carbocation, but instead bumped into one of the nearby hydrogens, what might happen is it would abstract that hydrogen, cause the carbon-hydrogen bond to become a carbon-carbon double bond, and then that would lead to a new product, and I would term that the Hofmann product, or a Hofmann product. There are going to be multiple Hofmann products in this case. So that's one thing that could happen at this stage. Notice, again, that there are no hydrogens over at this beta position, so it's not possible to do an elimination in that direction. However, we have a carbocation, so we could do a carbocation rearrangement here, do an alkyl shift, and move that methyl over. This position was the original alpha position, this position was the original beta position, and this now was a original beta position, but the methyl moved, and so at this moment, this beta position contains a carbocation, and originally there was one hydrogen at the alpha position not drawn, but I'll go ahead and draw him in now, and so he is hanging out right there. Now, of course, now that the carbocation is there, then the carbocation now becomes the alpha position, and I would need to examine the nearby carbons for potential hydrogens, and of course, both carbons near the carbocation contain plenty of beta hydrogens for potential abstraction. And again, I have lots and lots and lots of water floating around, so I could imagine using any of these waters to do a deprotonation at this stage, and if I come along and simply abstract that hydrogen and cause that carbon-hydrogen bond to collapse down to become a double bond, then I would now be forming a new, also Hofmann product. But there is one new way that we could attack, and that is that this water could instead bump into this hydrogen right here, which would lead to an internal double bond, and that would definitely be the Zaitsev product. And so you see the problem. If you start with this and say predict all the products, well, you're going to make a lot of things. You're going to first destroy the stereochemistry because you go through this carbocation, and then when the water adds back in, there's no reason why it needs to add from the top, so you could get the top and the bottom, so you could just create the racemized alcohol. But But even once you start thinking in terms of elimination products, well, the water could attack here originally, which would lead to this Hofmann product, or you could do a carbocation rearrangement, and then there's lots of hydrogens nearby that you could pull off, 6, and each of those would lead to a different Hofmann product than the original, but still a Hofmann. And then there's one and only one hydrogen that, if you abstract, leads to the most stable of all of the alkenes that you could make. And so yes, you can in fact make the Zaitsev product, but in order for that to happen, first this has to happen, this has to leave, then you have to do a rearrangement, and then specifically the water needs to bump into the one hydrogen that leads to the lowest energy product. So can you make this product? Yes. Is there a thermodynamic sink here? Does it want to get here? Yes. Are all these steps potential equilibrium steps so that you could funnel and end up here? Yes. So is the Zaitsev favored? Yes. Is it going to be the major product? Probably yes. Are you going to make a whole mess of other things? Definitely yes. It's going to be unselective, even if you're at least somewhat selective for the lowest energy overall final product. And keep in mind that what has to happen here is that a lot of things need to happen, but since this is all just kind of sitting here, there's going to be a preference for it to eventually find the lowest energy pathway, which again is to funnel here, because this tertiary is explicitly lower in energy than the secondary. And then it's going to find its way to the lowest energy sink also, because pulling that off leads to a better product than pulling one of these off. On the other hand, these are still relatively high energy intermediates. You have pluses on carbons that lack octets. They don't want to hang out like that. And bumping into them in the right way with these waters will lead to other products as well. So it's going to try to find its way to the lowest energy product, but there's a lot of ways in which this could get derailed and make other things. So, core idea here. E1 eliminations are messy, especially if you have carbocation rearrangements possible. You're definitely going to be favoring Zaitsev products because those are the lowest energy thermodynamic products, but there's no particular reason why they need to go there selectively. Instead, what you're probably going to do is make a little bit of everything, hopefully more of the Zaitsev than anything else.